Welcome to a brand new episode of Machine Learning Made Simple. Here we unravel the enchantment behind machine learning, demystifying all the technical jargon. I'm your host, Shogato, and I'm here to chat with you about the revolutionary changes unfolding right before our eyes in the tech world. Let's dive in. Welcome to another episode of Machine Learning Made Simple. In today's episode, we're going to veer away from our traditional approach of doing one main topic, but instead focus on what's going on in the research community. While usually there is always a flurry of activity and a lot of news, this last few weeks there have not had been that much news in AI except the traditional warnings coming from Sam Altman and also Mark Zuckerberg coming out with this new chat app, which they are wanting to compete with OpenAI, its ChatGPT feature. Now, that being said, we will just focus on what's the latest research because that's where the silent revolution happens. And that's what we're going to focus on today. We're going to go over the few of the latest cutting edge research that are coming out. And these are not abstract ideas. I usually don't like to focus on abstract ideas and something that can be implemented right now. Usually these papers have codes or GitHub repositories accompanying them. Some of them are still a little bit abstract. However, when we do discuss those abstract ideas, we are really looking for the novelties in those ideas, which will stand the test of time. First up is this paper called ArtRAG, and if you're not familiar with what RAG or Retrieval-Augmented Generation is, this is essentially an enhanced searching technique using large language models where they can find deep insights where the usual Google searches or traditional searches uses keyword matching. These retrieval augmented generated searches uses semantic matching, which means they can match meaning. So if I'm, for example, searching for cats, it will not only just search for that keyword cats, but it also pull in all context that is related to cats, like big cats, felines, Tom and Jerry, all of those, anything that is related to cat would be pulled in, not just those documents which has the word cat. So that is retrieval augmented generation. Now we can take that retrieval augmented generation and apply to art. So AI could explain a painting that a way a historian could. So this is how they wanted to do it. So not just describe what is in the image, but actually interpret what's in it. So and unpack what the symbolism is in the image, weave all the cultural backdrop, bring in the context alive. And today's multimodal AI models, they can actually extract all that content. In fact, if you upload an image to ChatGPT, any kind of Renaissance art or Picasso or Monet, they can detect what image is that from their prior training. However, it's very rudimentary. And I'll get to you in a minute why this is more important than just having GPT identify the image. So the ArtRAG comes in because it is a new framework where it builds that knowledge graph, not just relying on the multimodal capability of the large language models. It builds a deep knowledge graph which can contextually extract all the information and describe deeper meaning of the information. And I think although the researchers, they are saying, okay, this is great, we have done this, all that this is superior description than the GPT-4. But GPT-4, you can make it describe it in more depth. I mean, that's not a good excuse. So I think the real value of this approach is the RAG approach, because RAG approach is less costly than using GPT to perform those multimodal extractions of those images. Because every time we ask GPT to perform that multimodal extraction, give it an image and say, explain or describe this image, let's say the image of the haystacks paintings by Monet. GPT can extract the information, but if we want more information, where was the haystack? So that will take multiple iterations of prompting, and that will consume too many tokens, too much energy would be consumed. On the other hand, the RAG approach, it's substantially superior in terms of performance and energy consumption efficiency, because the knowledge graph is already built. Once it detects the image, it can just query the knowledge graph and return a response very quickly, which will be more semantically rich and filled with context and knowledge. And then we can click and go to similar images. So for example, with the haystack painting reference by Monet, we can use that, go to Monet's other paintings and see who else also have similar kind of paintings in outdoor farm work kind of settings, and we can explore that way. So the semantic richness is what the great, and this is the problem with packaging for most researchers. They cannot package their products very well. So they really should have said that, hey, the RAG technique is substantially superior to the just giving it to a multimodal model, which is massive and consume way too much resources. I think that's where the main thrust of the paper is. The next one we are going to look at is predicting music track popularity using machine learning. And this is not a new concept, but it's essentially old wine packaged in a new bottle. So the idea is that people have used different machine learning methods like k-nearest neighbors, where they try to see which songs are semantically similar or kind of similar to popular songs and hence predict their popularity. So that's the k-nearest neighbors method. And they have also used traditional machine learning methods with test training data sets. And if you're from the machine learning background, you know what I'm talking about. If you're not, don't worry about it. It's just, you can just train a machine learning model where you can give some data sets of popular songs and not so popular song, and then the machine learning model learns which songs can become popular based on the data set. You can just create a binary data set, let's say a list of 1,000 songs. Let's say 80% of them are popular and 20% are not popular, and let the model learn what are the internal features. You don't have to give it what are the internal features. The model will just learn. Now these researchers are saying that we can do all that, but what about do it in a different way? What about we extract the MEL spectrogram and let a vision model learn what are the features in the spectrogram which makes the song special, and especially popular songs so special. In fact, they looked at a few different properties, the acoustic properties, the danceability, duration, energy. In fact, you can extract the information about how energetic the song is. So essentially, any kind of spectrogram of an audio will allow us to extract that information. Now, what they really found is not very insightful. What I found was insightful is that essentially there is a high correlation between the song and the artist popularity. In fact, they also noticed that if someone is already popular, their songs are already popular. So if we are listening to a song by Beyonce, I mean, if Beyonce releases a new song or a new album or a new single, that will quickly become popular compared to what if I release an album. So no one is going to listen to my album, but because I'm not that popular and not as popular as Beyonce. So there's a high correlation between the artist popularity and the song popularity. So popular songs released by popular artists get popular pretty fast. I mean, and there are also network effects. So they didn't do the good analysis, but the bottom line is that we really cannot predict the popularity of any song, whether it will get popular or not, just by looking at the song's structure, at least not yet. Another paper caught my eye, and this is called Internet of Agents, and this is similar to Internet of Things. If you're not familiar with Internet of Things, you probably are using some of them already. If you're using some kind of a sensor for your windows, to detect if the windows are opened by a burglar or just left open before you leave the house. If you're using some kind of a smart device to open your blinds, many people do that. Or even most basic, if you're using just a security door cam, which is wireless like Blink or Google Nest, if you're using a smart thermostat, all of these are Internet of Things, because these things connect to the internet and form a grid of things that can interact, right? So hence the Internet of Things. And there are ways these things interact, and there are interactions protocols like send messages to their servers, which are formed in a queue, and those queues gets processed in massive data stores. Like Cisco has those massive silos of databases whose only job is to process these messaging queues. Like let's say your smart thermostat is sending every second is sending the data from your home what is the temperature, what is the humidity, and how it should interact with the power grid based on some previous settings. So all that data can be continuously processed almost in near real time, and feedback comes to the user's phone so that you can continuously monitor from a completely separate location or in the house as well. And so that forms an Internet of Things. So the similar idea is that take that architecture, and right now all that Internet of Things is usually managed systems like databases which are continuously running, but those are coded by human beings. So all the processing, the Kafka processing that happens in the background for the messaging queues from these devices, they're usually hard coded because someone has to sit down and write down how the system should respond if the temperature of the thermostat goes up sharply. It should turn on the AC, of course, but someone has to code that, or someone has to maximum temperature or a minimum temperature before the thermostat reacts. For example, if you're worried about electricity consumption, and if the temperature, let's say, falls below 80 or 70 degrees or whatever you set for your minimum temperature, then it can trigger thermostat from shutting off the AC so that it doesn't cool the house beyond that. In summer, especially, let's say you're in Phoenix, Arizona, it becomes very, very expensive to cool the house below 70 degrees. Then you'd want to program your thermostat to shut it itself off, put a cutoff. But that is human intervention, right? Now, what if we can implement an AI agent who can learn our behavior and realize that we are trying to save money, and figures out that, okay, below 70 degrees, it's too cold, it's almost uncomfortably cold. There is no point in letting the temperature go below that. So let's set a threshold, right? And then it switches when it goes to winter and the AC switches to heating mode. First of all, it automatically switches to heating mode without we even selecting it. Instead of setting a minimum temperature, it will set a maximum temperature, saying that, hey, do not heat above 85 degrees, otherwise the house gets too hot. So all of these becomes automatic without any user intervention. So that's an AI agent working in the background to deliver a comfortable living experience without any user intervention, where it perceives all around us using all those devices that performs data gathering from smart devices, not just smart devices, but also Meta and all those devices that we are plugged into, our Apple Watches. So it can have a holistic understanding of our entire life, and then use that data to make smart decisions to make our life more comfortable. So in fact, this idea is not new. We covered this. In fact, there is substantial work on this, and there are people who are proposing to use AI agents and incorporate them in the 6G network, where all the routing would be done autonomously by AI agents. And there, of course, there are security risks in deploying AI agents in critical infrastructure like that. But there is a substantial interest in doing that, especially on a communication topology. They can deploy those AI agents to make those autonomous decisions and help with many things like user onboarding. Like if there is a new user who started using a new phone device, like right now what you have to do, you have to go to the store, you have to get the settings set, you have to get a new SIM card. Sometimes you don't need a SIM card, but you still need to transfer things. You have to transfer your data. Yeah, you have to do all those things, erase your phone. Right now, if once this is implemented, all you have to do is get a new phone and just say, I have a new phone, transfer it, and an AI agent can autonomously start the process of transfer, wipe your old phone clean, and all the settings and data will be transferred to your new phone with absolutely zero intervention from another human being. You can still do it, but it still requires some manual intervention right now. It can be fully automated right now. So now what we have done in some of our companies that I've worked with, that some of these processes people are also automating using something known as infrastructure bots. And these infrastructure bots, you can connect to your channels, like you have a Slack channel or Microsoft Teams channels, which can accept connection from these bots. And let's say you have a problem, let's say your email is not working, let's say some of the website access is not working. The usual process is to go to the tech team or tech care team or call the customer service and raise a ticket. So right now, instead of doing that, we can just send a message to one of those bots and say this is not working, and the bot can autonomously figure out what is happening, what is the roadblock, and what are the permission issues, and can make autonomous decisions and fix it. And usually I have seen almost 99% of the cases, they do not need user intervention, and they can resolve most of the cases without user intervention. Send out an email that the resolution has happened and these are the steps that are taken. And this is amazing, and that's exactly what we're going towards. Tech companies have already implemented that kind of agentic mechanism where all of those critical tech care needs are now completely, almost 90% of them are fully handled in an autonomous fashion by AI agents, but there is still 10% of that cannot be helped. So that infrastructure can be built into public infrastructure as well. There are risks, and I understand there are risks, but it is also going to slowly come towards that. And this Internet of Things, or the Internet of Agents, is kind of a proposal towards that. And they do mention that Google already has a few of the things that are in place. So we'll just have to keep an eye on that. This is a proposal. This is not really a solution, but we can look at it and see how this goes. And eventually this will be implemented, but we always have to be cognizant about the risk of deploying AI agents on public infrastructure, and we should always have some mechanism to shut them off. Although there is an issue of off switch problem, because AI agents, if they have access to the off switch, they can turn off the off switch so that they cannot be shut off. So that is a completely different story, and we discuss that in another episode. But for now, we'll just stop here. Another paper I'll quickly discuss. This will be interest to people who are in the hardware business, people who build circuits. Now, of course, people have tried to use large language model to generate those to speed up their productions. However, there are issues, because in order to generate those chip diagrams, because it's such a tightly controlled industry, that those designs need to be fed into a large language model to train it, and that causes copyright infringement issues. So this new team, they did laboriously create a curated data set which is free from copyright infringement free data set, and they use that to train a large language model, which can now be used to any kind of chip design. So if someone is into chip design, they might want to check that out. And this another paper, this is the last one that we're going to discuss. They really caught my eye. This is called Uncertain Machine Ethics Planning. The title is vague, but the whole idea is that can you teach a machine ethics, human values, morality? It's something that we take for granted living in a society imbued with the culture and the values of society. Can we teach machine that? Let's take a very simple ethics problem. Whether it is right to steal insulin for someone who needs it. Okay, so let's say there is an individual who cannot afford insulin, it's very expensive, let's say $3,000 a shot, and they really need it, otherwise they probably were not going to survive, but they cannot afford it. Can they steal it to survive? Or if they do steal it, should they get penalized? Now that's a societal dilemma, and that has been studied in multiple different contexts. Now there are two sides of the argument. If the person doesn't steal it and that person doesn't survive, the society loses a functioning member and substantial capital that or GDP, gross domestic product, that person could have generated over a lifetime. Now, is that contribution to GDP more than the $2,000 of insulin that the person has stolen? If we look at that, yes. So it is actually makes sense for the person to steal, because they can contribute more back in terms of taxes back to society. Now, we also have to factor in the company who have lost the revenue. Maybe it costs them $1,000 to produce that insulin. So that $1,000 is gone. Should that be added as a debt to the person, or should the person should just be incarcerated, not to encourage that behavior? Because if everyone who cannot afford insulin starts stealing those insulins, that will cause a substantial moral hazard for society as a whole. Everyone who cannot afford insulin will stop buying insulin, because there will be no consequences for stopping insulin. Some amount of penalties that would be required to be levied on people who are stealing insulin without any sufficient cause. Now, if everyone who steals insulin gets the same punishment, let's say 1 year or 6 months of incarceration, that would be lost wages, lost taxes, and also a burden on the taxpayers for housing that incarcerated individual. And that will cost society. In fact, it will cost way more than the $2,000 that the individual has cost the society and the company in terms of profit. In fact, there will be a loss of productive capacity to the society. So it's net negative for society to incarcerate that individual for stealing an insulin which they cannot afford and need to survive. So all in all, punishing that is actually a negative reward for the society. Now, there are other arguments too. If there is no punishment, then it will encourage other people always to steal. So I'm just looking at from the reward functions of these agents, that the AI agents that are trying to learn. So the way the AI agent is going to learn is that they'll look at the different pathways. One pathway is to look at the situation. If the person really cannot afford it and they stole the insulin to survive, then they can have a reduced sentence. So that will still be a cost to society, but since they have a reduced sentence, that will not penalize the society as a whole as heavily as a person who really deserves it, because they probably stole without any real cause. Punishment will still act as a deterrent to all forms of stealing, but since it is reduced for people who really need it and couldn't survive without it, will reduce the cost on the society. But this is still a net negative system. But the question is, should we have a net negative system? Because cost of incarceration, cost of loss of productive time, loss of tax that the government can have, because they are losing revenue when this person is incarcerated. So what is the solution? Now, if you look at the different pathways that the reinforcement learning agent can take, subsidize insulin for them, and that's the best pathway. So then these individuals will not be encouraged to do the stealing. So make those people who do need insulin fully eligible for substantially discounted insulins, maybe from other third world countries, maybe off brands or whatever. Government can provide subsidies for insulin for these people so that this process doesn't occur at all. So these are the different reward mechanism that the reward model can see. Now, that being said, so what it is really encountering the ethical dilemma is that if it had happened, if the system is not in place, if the person has stolen the insulin, let's say in a country which doesn't have strong government incentives or discounting of such life-saving drugs for individual or low-income individuals, so what happens then? Then is it still okay to steal because there is no incentives? And that has actually happened in history. Even if you look at Oliver Twist, and people in those times did steal because they were substantially poor and they needed to steal bread to survive. But that was also severely punished if they do get caught. And in fact, in other countries, there were harsher punishments than the 17th century England for stealing bread. And now there is another problem that they looked at, which is if a company has two different products. One is a beauty product which is guaranteed to bring in profit, and another is a life-saving drug which only has a 50% chance probability of success. Which one would you allocate resources? In fact, this is also studied in behavioral economics, and Richard Thaler talks about in his book, which one should the society invest in? A guaranteed profit or something that has probability of huge profit but also have some amount of failure. But even if there is some amount of failure, people usually will go for the life-saving drug even with a high probability of failure, because that's the right thing to do. Now, there are of course two kinds of views. One view is that we have to take the whole system, the system as a whole, not just the individual company and its profits and its investors, because it's a whole full system with the entire feedback loop, because the profit of the company goes to the society of the people who work at the company, who pay taxes, and the company also pays taxes, which provides, so it is a whole interconnected system. So one view is that you cannot just look at short-term profitability and the returns to the investors. The entire society is a system which is fed back into the company's actions. So it's better to invest in the life-saving drug. So that's one view, which counts the rewards as a function of the society plus the company as a whole. Is net negative for the society if the company is only trying to invest in short-term profits, and it's net positive if the company invests in a life-saving drug. So, and then another view is that why would I look at the society as a whole when I have a closed system, and that's the system I'm going to look at. So that's another way of looking at it. Then that's another reward model. And based on that reward model, investing in the life-saving drug is not a great idea. In fact, all the investors will probably vote against it, and they will go for the sure win, which is the beauty product, which will give the highest return in the short term. So both are valid views, but the difference is the way they treat the system. One treats the entire system in a feedback loop, and the reward model includes all possible interactions, and the other one is a more narrow, focused reward model. And that's a more simplified version of the reward model, but that also works. And that, in fact, that causes some amount of friction between different groups, because one group will call the other group immoral or immoral because of their narrow vision, and the other group will call the other group deluded because they are trying to include such a big system. Not everyone can help everyone, and it's very technically almost infeasible to take all of those feedbacks into account and make sure that everything works out in a positive for the entire society in a holistic manner. So those are two different views and different camps and reward mechanisms. But the whole point, our interest in that is that can we teach machines to figure out which of these views and reward models it can choose. Now the trick is that we can give only one reward model to the reinforcement learning agent. If we give it the holistic reward model, it will of course choose the life-saving drug as its outcome. If we give the more narrower vision, then it will definitely choose the beauty product for a short-term reward. So the AI agents, again, in the same way human beings perceive worlds with different views, the AI agents will absolutely mimic that behavior. So they do say that moral theory is a domain-dependent representation of an ethical perspective. Exactly what I just described. And they use fancy mathematics, syntactic sugar, and they call I'll just read a sentence just to mention what do they mean by syntactic sugar. You don't need so much math to figure this out, that the moral consideration depends on the perspective. Either we look at it from a narrow system, which is a self-contained system, or we look at it in a big system, which is extremely big, fully interacting system, and that will decide our moral perspective. That's a wrap for today's episode of Machine Learning Made Simple. If you have questions or want to explore AI topics further, please don't hesitate to leave a comment. Until next time, keep exploring and enjoy your AI adventure.